Hello and welcome to this pre-recorded presentation of my PQCrypto 2020 article, Practical Cryptanalysis of k-ary Cstar, presented by myself, Daniel Smith-Tone. The article and this presentation present a total break of the k-ary Cstar cryptosystem, a multivariate cryptosystem. Multivariate cryptosystems use as public keys large, massively multivariate systems of nonlinear equations. The idea behind this is that it is well known that the problem of determining the satisfiability of a system of nonlinear multivariate equations over a finite field is NP-complete. Thus, there is hope that this task may be difficult even for quantum computers. Still, it is difficult in practice to construct an efficiently invertible multivariate map without revealing the structure used for efficient inversion. One common technique is to use multivariate representations of univariate functions over an extension field. Given a univariate function f over the degree n extension e of f, one can construct the vector-valued function, denoted here by capital F, over the small field fq. To hide the choice of representation of this map, one composes on the left and the right linear transformations that mix the input variables and mix the output equations. In this way, one constructs the public key p as the composition of these three component maps, which we will call T, F, and U. Since the univariate map f is chosen to be efficiently invertible, the legitimate user can then invert the public key by inverting sequentially each of the components. The first cryptosystem of this form was the Imai Matsumoto cryptosystem, which is commonly called Cstar. In this case, the univariate map f is the map f of x equals x to the q to the theta plus 1. This map is fq quadratic because it is the product of x with a Frobenius power of x, both linear functions of x. To make the map invertible, it is only necessary to choose theta so that the exponent is coprime with the order of the unit group in the extension field. In such a case, it is easy to invert the map by finding the decryption exponent. The Cstar cryptosystem was broken in the 90s via a linearization equations attack by Pataran. At this point, many different variations on this fundamental idea of the big field multivariate cryptosystem were proposed, many of which have since been broken. Perhaps the closest relative to Cstar is k-ary Cstar. The idea here is to simply replace the fq quadratic map with a more general power function. If we want total degree k in the multivariate representation over the small field, then we use an exponent whose q-ary expansion is binary of Hamming weight k. The reason that the exponent must be binary is that everything is happening in a field of characteristic 2 for the function to even be bijective, and we can always choose to represent everything over GF2 if we want. In April 2005, Crypto Challenge 11 was published with a €5,000 prize for anyone who could break the scheme by the end of that year. The challenge parameters use k equals 4, so a biquadratic public key over the small field GF16 with 25 variables and equations. In June of the same year, Fougere presented a break of a toy instance of the scheme over GF32 with 16 variables and equations using the F4 algorithm. The original challenge already alluded to this result in its documentation. Still, breaking this small instance required 96 CPU hours on reasonably fast machines. As a result, Fougere conjectured that for values of n of at least 26, that 80-bit security can be achieved. More recently, about a year and a half ago, Felke revisited Crypto Challenge 11 and concluded that it can be broken in 2 to the 52 field operations with about 1.3 terabits of memory. It is then conjectured that setting n to 100 achieves 80-bit security. Before we move on to the results of this work, I want to recall the attack on Sflash. The attack serves as inspiration for breaking k-ary Cstar. Sflash is a Cstar minus scheme, which simply means that you remove some of the equations before publishing the key. We denote that here with a capital Pi. When convenient, to save space, we will use the pi as a subscript, otherwise we will use it explicitly. The key thing we need to note is that Sflash was broken by a differential attack, not by the direct algebraic methods previously attempted with k-ary Cstar. Here we can see the definition of the symmetrized discrete differential. If we consider the Cstar monomial, then the differential takes the form of the third line here. We can see that this formula is linear in both the variable a and in x. If we translate this to the vector-valued function over the small field, we have a function for each of the n-coordinates that must be then bilinear. The Cstar monomial is special in that its differential satisfies this symmetric relation with respect to elements of the extension field. We can see that the symmetric product of sigma with the inputs of the differential can be factored out. Since multiplication by elements of E is a linear action with respect to the small field, this multiplicative differential symmetry over the extension field translates directly into a linear differential symmetry over the small field. Now let's call P a full rank key and P pi the public key with equations removed by the projection pi. We can define a linear map in sigma as the conjugation by U inverse of the multiplication by sigma map, M sigma, over some standard basis. We then symmetrically apply this map to the inputs of the public differential. Using the definition of P pi and the linearity of the differential operator, we can pull the pi and t maps to the front and place U in front of each input. Now we can use the definition of n sigma to cancel with a U to get this expression. Now notice that the multiplication map is symmetrically applied to the inputs of the differential of capital F. Just like the differential of the small f, we can pass this multiplication map through df to get this expression. At this point, you should notice that the end of this line looks almost like the differential of the full rank P. Interposing the right map, we get exactly the differential of P. All of the stuff on the left is linear depending on the value of sigma, so we may write the entire expression as a linear function of the differential of the full rank key. Thus we get the following equation. This equation serves as a criterion for finding a map of the form n sigma. Specifically, you let the coefficients of the map n sigma be unknowns and assert that the first few coordinates of the left-hand side are in the span of the known public differential coordinates. It is very easy and practical to solve for such a map, and we can prove that other than in a certain number of exceptional cases, that the map we derive is exactly the conjugate of a multiplication. Once we have such a map in sigma, we can compose it with the public key, and with a few lines of calculation that are similar to what we performed with the differential, we see that we recover a linear combination of polynomials from the full rank key. At this point, it is very likely that we can recover a full rank key and apply Patarin's linearization equations attack. Thus, Sflash is broken and badly. But wait a minute. The linear combination of the full rank key looks like it has a special form. If we forget the projection for a second, we can see that the linear combination of the Cstar public key we recover is a conjugate of a multiplication map. Specifically, it is now conjugation by t instead of by U inverse, and then the multiplication is by f of sigma instead of by sigma. So what we have discovered is that P provides a nonlinear map between representations of the extension field E relative to different bases corresponding to the rows of U inverse or to the rows of T. Therefore, we can use the public key to derive canonical bases for these two representations of E with respect to a particular element, sigma. We will try to be consistent and call these maps N and Z respectively. Notice that we can recover Z sigma from ZF of sigma by raising it to the appropriate power H that we mentioned earlier. Since there are very few possibilities for what H could be, we can just try each one. Now, using this tool, it is easy to derive another message recovery attack on Cstar. I'd like to comment at this point that I feel like this attack is more or less known by many in the community. I know that I've known about it for at least around 12 years, and I think that many other experts know it also, perhaps modulo some of the details. So we have a ciphertext Y, and we want to recover a plaintext X. We first use the differential attack to recover in sigma, just as in Sflash. Then we find an anchor by encrypting a random plaintext X0 to produce the ciphertext Y0. We then find the unique linear map Z tau in the Z basis that sends Y0 to Y. Using the same linear combination we used to produce Z tau from its basis, we form N tau. We can then recover in f inverse of tau by raising this map to the proper exponent h. Finally, we recover the plaintext by multiplying x0 by this particular map. So why does this work? It is because P sends the map in sigma to the map zf sigma, or in reverse, it sends z tau to n f inverse of tau. So the correct input to get y is in f inverse of tau applied to x0. But more than this, we can turn this technique into more of a key recovery attack in the sense of getting a key of the same form as a legitimate user. To do this, we find a root over the extension e of the minimal polynomial of our recovered linear map in sigma. We know that tau then must be some conjugate of sigma inside of e. We then solve for maps u hat and t hat that translate between some standard basis for multiplication maps and the n and z bases. When we have done this, we can compose the inverses of these maps with the public key to get a multiplicative function p hat, which must be a multiple in e of the private function f. Now we do something similar to what we did before. We fix an arbitrary anchor, an input-output pair x0, y0, for our function p hat. Then with the composition of a pair of multiplication maps involving x0 and y0, we recover a compatible private key. So why does this work? It is because the way we defined the maps u hat and t hat, passing a multiplication map from the right to the left past u composed with u hat inverse, applies some unknown action from the Galois group that depends on the choice we made of the conjugate tau of sigma. And then we pass again another multiplication map from the right to the left past t hat inverse composed with t. That applies the inverse of that Galois action. Everything else just cancels out. But wait another minute. We didn't use the fact that f was quadratic anywhere. We only used the fact that f had a differential symmetry allowing us to recover a multiplication map. It is definitely not the case that differential symmetry requires the map to be quadratic. It is easy to define a higher order differential. Recall that the differential definition is symmetric, so the differential of f of x is symmetric in the variables a and x. So then consider one of those variables to be constant and take the differential with respect to the other. By symmetry, you must get the same answer. So taking higher order differentials is well defined. You just have to add an extra variable each time you take a differential. So the third differential of an fq cubic function, for example, will be trilinear. As an illustration of this, consider this particular 3-ary Cstar monomial map. The first differential is symmetric, although it's quadratic in one of the variables for every term. But it doesn't matter which variable we consider now, taking the differential results in the bottom line, which is symmetric and trilinear in the three variables a, b, and x. Moreover, it is a straightforward calculation to show that the natural analog of the differential symmetry we considered before exists for this k and for any k. In fact, if anything, the attack gets easier as k increases. When k equals 2, as in the standard C* case, the differential provides 2 tensors. When k is equal to 3, the second differential provides 3 tensors. When k is equal to 4, the third differential provides 4 tensors, and so on. So as soon as k is greater than 2, you are getting a lot more information with each coordinate. In fact, if k is greater than 2, you only require 2 coordinates of the differential in order to solve for an n sigma. When k is larger than 3, we only need the first coordinate. I think n equals 9 is sufficient. In the article, we show that the coefficients of the differential relation can be derived linearly from the public key, so the entire attack only requires the ability to solve linear systems. The largest of these linear systems is typically the derivation of the differential relation itself. The entire key recovery for k-ary C* is order n squared times n choose k squared, which if you think about it is only on the order of about the square of the cost of simply evaluating the incredibly massive public key. I made the absolute simplest possible implementation of this attack and applied it to the Crypto Challenge 11, and broke it in under 10 minutes on what I can only assume is an ancient steam-powered Apache server at my university. I did nothing clever and just used symbolic algebra over a polynomial ring whose coefficients are polynomials of polynomials of polynomials. If it were not so tedious, I could have implemented the entire attack as a linear system, and it would have taken about 2 to the 38 field operations, or about 2 to the 43 bit operations. Then, in regard to Felke's improved version using 100 variables, this attack requires still only about 2 to the 57 field operations, which translates to about 2 to the 62 bit operations, still well short of 2 to the 80 bit operations as the claim was. Also in the article, we outline a great deal more information to attempt to resolve all of the unanswered questions along this line of reasoning. We present a classification of all functions for which this technique is applicable and thereby prove that a non-trivial projection, for example, on the input prevents the attack. Of course, you would likely still need to do some more stuff. You'd need to remove equations also, that is, do the minus modifier in order to avoid an attack like that on square. Also presented in the appendix is a detailed example of the entire key recovery operation on a toy example. So finally, what can we learn from all of this? Well, it seems that increasing the degree of Cstar did not have any positive effect at all on the scheme. If anything, it makes the scheme somewhat weaker than Cstar in the sense that fewer coordinates of the public key are required to actually affect an attack on the scheme. We have seen this sort of phenomenon with other schemes too, like HFE and with the simple matrix encryption scheme. Both of these schemes have had higher degree analogs proposed in the hopes that they would improve security or maybe even provide provable security. And in both cases, the schemes ended up being weaker than the original. This pattern seems to suggest that degree increasing modifications of schemes may be a bad idea in general. So thank you for surviving until the end of this presentation, and I hope you enjoy the rest of the conference.